As a Smith chart example, we're going to do problem 2.53, which is a 50 ohm transmission line is terminated in a load with the load impedance equals 50 plus J 25 ohms. And we're asked to use the Smith chart to find a lot of things, including the reflection coefficient, the standing wave ratio, the input impedance, and admittance at 0.35 wavelengths from the load, the shortest line length for which the input impedance is purely resistive, and the position of the first voltage maximum from the load. So let's walk through all of those things one at a time. First of all, in order to do anything with this problem, we need to normalize that load impedance and plot it on the Smith chart. So to do that, we divide the load impedance by the characteristic impedance, and that would give us 1 plus J 0.5, no longer in ohms because it's normalized, so it doesn't have any units. To plot that on the Smith chart, we find along the real line the circle where the real part equals 1, so this is the R equals 1 circle, and then we go up along it until we get to imaginary part equals 0.5, which is right here between 0.4 and 0.6. So there's that. How do we figure out the reflection coefficient from this? Well, the distance from that point to the center of the Smith chart is the magnitude of the reflection coefficient, and the phase we can read off the edge of the Smith chart at that angle. So let's measure the distance first and then go down to the scale along the bottom of the Smith chart to figure out what that reflection coefficient value works out to be. All right, so there's that. Down here at the bottom of the Smith chart, I have reflection coefficient, E or I, that's voltage or current. So the reflection coefficient magnitude is, looks like about 0.24. Maybe 0.25 depending, but I'm gonna say 0.24 because that's what it looks like. So the reflection coefficient, and this is part A, is 0.24 at some angle that we haven't determined yet. So let's figure out what that angle is. We take the ruler, and draw a line through the center of the Smith chart and our impedance point to read off the angle of that reflection coefficient. And the angle that we get is, looking right here at these labels, angle of reflection coefficient in degrees is the second scale out. So not this one, but this one. And we are between 70 and 80. So that looks like an angle of about 75, 76 degrees. I'm going to say 75. Angle 75 degrees. That's our reflection coefficient. Done. To find the standing wave ratio for this thing, we take this distance, measure it again. Measure twice, cut once is always true. Good, my compass is still set to the same size. Then we go down here and look at the scale that says SWR. We want to read the linear scale, not the dB one, so that's the top one. And it looks like our SWR is about 1.7. For part C, we are asked to find the input impedance at 0.35 wavelengths from the load. How do we find that? First of all, we're going to need to draw the constant reflection coefficient circle. So again, adjust my compass size so it's just right. Then I'm going to draw a circle. My compass doesn't draw very dark lines, so it might be hard for you to see this, but I am drawing a circle that is a constant distance from the origin of the Smith chart right here. Then I'm going to look at the wavelengths toward generator scale, that's the outermost one, and figure out what my start point is, which it looks like it is 0.146. So I'm starting at 0.146 wavelengths, and then I'm going to add 0.35 wavelengths. Which means that I need to go to 0.496 wavelengths on the Smith chart. So that's over here, almost but not quite on the left-hand side of the real line. So 0.49, 0.496 gets me to right there. So I take my ruler, I draw a line through that point and the center of the Smith chart, with that all lined up. The normalized input impedance at that point is where that line crosses my circle of constant reflection coefficient. It is between 0.6 and 0.65 on the real line, and not even 0.05 on the imaginary line. So normalized Zn is, I'm going to say 0.62 minus J 0.02. And to find the actual input impedance at that location, I need to multiply that by 50 ohms. So 0.62 times 50 is 31 plus, oops, that's a minus actually, minus J. 50 times 0.02 is actually just 1, so it's 31 minus J 1 ohms. Technically you wouldn't have to write the 1, but I wanted to make it clear that it is in fact 1 ohm. That's my input impedance Zn at 0.35 wavelengths. For part D, we're asked to find the input admittance at the same location. So we reflect across the Smith chart. If we'd been smart, we could have drawn this whole line all at once, and that might have given us slightly better precision, but that's okay. We reflect across the Smith chart because that's how you convert an impedance to an admittance on a Smith chart, and mark the place where that line crosses the real axis. And it looks like we are at real part equals 1.6 and imaginary part equals about 0.05. So normalized Yn is 1.6 plus J 0.05. Actual Yn is going to be that times the characteristic admittance. And the characteristic admittance is 1 over 50 ohms. 1.6 over 50 is 0.032, and 0.05 divided by 50 gets us 0.01 divided by 10, which is 0.001. So finally, it's getting a little messy, but Yn is 0.032 plus J 0.001 mhos For part E, we need to know the shortest distance for which the input impedance is purely resistive. And that's the distance from our start point to the real line, moving away from the load, so wavelengths toward generator. We're going to go that way. This real line is at a quarter wavelength, and our start point was at 0.146. So that distance is 0.25 minus 0.146, which is 0.104. So part E is 0.104 wavelengths. And part F is what is the position of the first voltage maximum from the load. Luckily, that location happened to be the right-hand side of the real axis, which is where the voltage maximum occurred, so that also is 0.104 wavelengths from the load.